How did we come to be here? Are we alone in the universe? How does the universe work? With these words, the official website of the James Webb Space Telescope greets its readers. These questions have not only recently begun to intrigue humanity. Of course, we have been seeking answers to them long before James Webb, and even long before the first telescope through which humans gazed at the sky. Yet, it is widely believed that with the launch of this space observatory, the answers to these fundamental questions might now be closer than ever. New possibilities. Perhaps these two words best describe what professional astronomers were expecting from Webb. And new discoveries. This is likely what we were all hoping for. Indeed, in just over 2 years of active operation, Webb has revealed numerous fascinating features we had not previously observed, such as those in planetary atmospheres, within nebulae, around interacting galaxies, and inside supernova remnants. However, the most groundbreaking findings have been its observations of the early universe, where astronomers aimed to see the very first structures into which matter coalesced. What they saw genuinely shocked many. Therefore, I decided to compile for you the most significant discoveries we have already made, thanks to the unprecedented sensitivity and resolution of the James Webb Telescope. In this first part, we will focus on the early universe, as it was this that the new telescope was meant to unveil for us. I believe we should start by understanding what the James Webb Space Telescope actually is. I realize you may have heard about it many times before, but it is important to briefly recap its key features before diving into the science. Today, it is the largest and most powerful space telescope ever built. Before its launch on Christmas Day 2021, Webb underwent a long and challenging journey, from design and construction to budget overruns and numerous launch delays. Many of the problems and difficulties were due to the need to invent numerous technologies from scratch. Webb is an infrared telescope designed to detect radiation that is invisible to our eyes, but crucial in astronomy. Infrared light can penetrate dense clouds of gas, allowing us to peer into early galaxies, forming planets, and uncover hidden details of nebulae. Additionally, the infrared radiation Webb observes is the stretched-out light of early, ancient galaxies. Over billions of years, as the universe expanded, visible and ultraviolet light lost energy, eventually reaching the mirrors of our telescopes as faint infrared signals. Since infrared radiation is thermal radiation, the telescope's designers had to figure out how to eliminate unnecessary heat sources, both within the telescope and in its surroundings. These heat sources could interfere with observations and obscure the faint signals from distant sources. To prevent thermal contamination, Webb was equipped with a 5-layer sunshield that reflects radiation not only from our sun, but also from our planet and its satellite. The telescope's home was strategically chosen to be the second Lagrange point in the Sun-Earth system, far from Earth's heat. Unlike Hubble, which orbits the Earth, Webb orbits the Sun, trailing along Earth's solar path. Shielded from external heat sources, the observatory's scientific instruments have cooled to -233 degrees Celsius, with the coldest, Miri, just 7 degrees above absolute zero. This ensures Webb's unprecedented sensitivity to infrared signals, including those arriving from the dawn of the universe. Without a doubt, the primary scientific justification for building the costly and revolutionary space telescope was to observe the early universe. This is its main mission, aiming to bring us closer to answering some of the profound questions displayed on the front page of its website. It's no surprise, then, that during its first 2 years, the cosmic dawn was among Webb's primary targets and drew particular attention. The period within the first few hundred million years after the Big Bang fascinates scientists because it marks the time when matter ignited the first stars, which, along with dust and gas, coalesced into the first galaxies. What did those galaxies look like? When and how exactly did they form? These are the questions scientists seek to answer to understand how the properties of galaxies evolve over time. The Hubble Space Telescope managed to peer into a universe about 500 million years old, uncovering galaxies that differ significantly from the familiar spirals and ellipticals. They are compact and lack well-defined shapes. Until 2022, Hubble held the record for the most distant known galaxy, GN-Z11. The 11 inches in its name corresponds to its redshift, which represents a universe about 400 million years old after the Big Bang. Personally, I find it more intuitive to discuss the age of the universe corresponding to a given redshift rather than distances in light years. This is because the actual distance to such an object can be tens of billions of light years. For GNZ 11, about 32 billion light years. Understandably, this can confuse people who know the speed of light is finite and that the universe's age is only 13.8 billion years. It might seem paradoxical, but these galaxies have indeed receded from us faster than the speed of light due to the universe's expansion. To avoid further confusion, I suggest we avoid discussing light years in the context of early universe objects. Instead, let's grow accustomed to using redshift, a measure of how much an object's spectrum shifts toward longer, redder wavelengths. Since the universe's expansion causes this stretching of light waves, redshift is the most accurate and unambiguous way to estimate distance for objects in the early universe. For convenience, whenever I mention a specific redshift value, I'll include information about the corresponding age of the universe. With the start of James Webb's scientific operations, GNZ 11 is no longer the record holder, now ranked 11th among the most distant galaxies. The top 10 are currently occupied by galaxies discovered by Webb during its early scientific programs. One such program, the JWST Advanced Deep Extragalactic Survey, already delivered new record breakers by September 2022. An international team of scientists pointed Webb at a region of the sky famous for Hubble's iconic deep field images. While Hubble required more than 20 days to collect enough light in this area, Webb accomplished it in just 20 hours. Webb uncovered hundreds of candidate galaxies with redshifts greater than 10. By October 2022, scientists had identified 4 among these with spectroscopically confirmed redshifts above 10. Among them, JWST 13.0, with a redshift of 13.2, became the new record holder, residing in a universe just 330 million years old. In fact, this record was short-lived, as a new remarkable distance milestone was reached in 2024. Within the same scientific program, early in 2023, scientists identified an intriguing object in their data. Initial estimates placed its redshift at around 14, already hinting at a new record. But what stood out even more was its exceptional brightness, far too bright for a galaxy in such an early universe. Given how little time had passed since the Big Bang, it seemed unlikely for a galaxy to have accumulated so many stars in such a short span. This left astronomers with 2 possibilities. Either the distance estimate was inaccurate, or something was fundamentally off with current galaxy formation models. When it comes to estimating distances, astronomers indeed face challenges. To briefly explain, scientists capture images of a region of the sky using instruments like NIRCam, which is equipped with various filters. Each filter only allows specific wavelengths of light to pass through, meaning a source's brightness appears differently through each. Astronomers measure the brightness of a galaxy in each filter and compare this data to models corresponding to different redshifts. The model that best matches the data suggests the likely redshift of the galaxy. This approach, called the photometric method, is highly efficient as it allows researchers to analyze vast areas of the sky and evaluate numerous sources simultaneously. However, the photometric method is not entirely precise. Objects in space can appear red not just due to cosmic expansion. For example, galaxies with a higher proportion of cooler stars or significant amounts of dust, obscuring certain wavelengths, can mimic the appearance of high redshift objects. Thus, 2 galaxies with similar filter-based colors could have entirely different redshifts. To confirm their estimates, researchers must rely on a more precise technique, spectroscopy. By splitting the light of a source into its components, they examine the absorption or emission lines of specific chemical elements, such as hydrogen. Comparing how much these lines shift toward redder wavelengths relative to their laboratory measurements allows scientists to determine the exact redshift. The drawback is that spectroscopic observations require extensive telescope time, often tens of hours for a single source, making this method costly and labor-intensive. It's no wonder that some candidates identified back in 2022 are still awaiting confirmation. But for the candidate with a photometric redshift of 14, the one we are now revisiting, the wait wasn't overly long. In January 2024, astronomers observed it for 10 hours using the NIRSpec instrument. The findings revealed that JWST 14.0 has a redshift of 14.32, making it the most distant galaxy ever observed at the time of this recording. We see this galaxy as it existed in a universe just 285 million years old, a truly breathtaking discovery. However, that's not all. The fascinating properties of this galaxy are no less striking than its age and distance. It's incredibly bright. To grasp just how bright, take a look at its spectrum compared to the spectrum of the previous record holder. It's astonishing that a galaxy with a redshift of 14.3, the farthest ever discovered, is 5 times brighter than a galaxy with a redshift of 13.2. Of course, one might assume that all this energy isn't coming from stars, but for instance, from a supermassive black hole at its center consuming matter. However, the researchers estimate the size of this object to be around 1,600 light-years. If the brightness were purely due to accretion onto a black hole, the source would appear far more compact than 1,600 light-years. Considering this brightness and size, the galaxy at that time might have contained a stellar mass equivalent to several hundred million suns. This is truly impressive, especially when we recall the universe's age, less than 300 million years. This raises a logical question. How could the universe produce such a large and massive galaxy in less than 300 million years? For context, current models of galaxy formation suggest it would take close to 1 billion years for a typical galaxy to accumulate hundreds of millions of sun-like stars. This suggests that JWST 14.0 is unlike the galaxies predicted by theories and modeled by supercomputers. Spectroscopic confirmation of its properties implies it's not alone. And indeed, it's not alone. Similar evidence for astonishingly large and bright galaxies emerged with the very first deep space images provided by the new observatory. Most of these are still candidates with unconfirmed redshifts, but they show impressive sizes and luminosity, indicating stellar masses ranging from tens of millions to 1 billion suns. For comparison, this is still much smaller than the Milky Way, but much larger than scientists had anticipated. At present, this is one of Webb's greatest discoveries and one of the biggest surprises it has delivered. As is often the case, some were quick to jump to hasty conclusions when these galactic oddities appeared in the data. Even among professional scientists, ideas emerged suggesting that the unexpected properties of early galaxies might point not to errors in our understanding of their evolution, but to flaws in our understanding of the universe itself. Perhaps the cosmological model known as lambda CDM is incorrect. There's no expansion, no dark matter, no dark energy, and perhaps even the Big Bang should be discarded. Indeed, if James Webb had revealed structures like the Milky Way or Andromeda, it might have compelled many to rethink the problem from the perspective of the Big Bang. But the fact is, these galaxies don't resemble those. They are still an order of magnitude smaller and dimmer compared to typical spiral or elliptical galaxies we're familiar with. In general, all galaxies with high redshifts are significantly less massive than the fully formed galaxies of the local universe. There are, of course, several non-cosmological explanations for why these oddities managed to produce so many stars so quickly. Firstly, we might have caught them at the very moment they entered a particularly active starburst phase. It's entirely possible that young galaxies don't grow slowly and steadily, but instead experience sharp, burst-like phases of star formation. Additionally, it's plausible that gas collapses into stars faster than we imagine. Back then, the universe was more compact, and matter had higher density, potentially allowing gas to collapse more intensively and more effectively counteract the repulsive forces that arise during heating. Or finally, these galaxies might simply be outliers, exceptions to the rule. They are bright, making them easier to spot in the early universe, but that doesn't mean they're representative of the galactic population of that time. Recall how it was with exoplanets. Initially, strange hot Jupiters were discovered, but later, with improved observation capabilities, it became clear that they weren't as common as initially thought. Of course, such shocking data from Webb already has not only hypothetical, but also more substantiated explanations that have been carefully studied. In particular, in this study, the authors demonstrated that at least some of these strange galaxies might appear bright, not because of the number of stars they contain, but due to the activity of black holes consuming matter. The friction of gas rapidly spinning in the accretion disk causes the material to heat up and emit light and heat. This additional radiation makes the galaxies appear brighter than they would if the light came solely from stars. However, this explanation doesn't seem to fit JWST 14 and other sources that appear too large to be solely powered by active black holes. Ultimately, another study showed that stars in dawn-of-time galaxies could indeed form in bursts, a concept known as starburst formation. This is not a hypothetical concept. Astronomers observe similar phenomena in the local universe, especially in low-mass galaxies, though the reasons for it remain unclear. One possibility is that due to the relatively small mass of such galaxies, supernovae can eject gas into the circumgalactic medium. Later, the gas returns, triggering a new cycle of star formation. The fact that this is not observed in large, fully formed galaxies might be related to their greater mass. With higher gravitational pull, supernovae cannot expel gas beyond the galaxy's boundaries, keeping it within. As a result, in massive structures like the Milky Way, stars form at a steady rate. Therefore, these shocking galaxies do not necessarily have to be massive. Their apparent brightness might be misleading, a result of enhanced luminosity caused by a wave of starburst activity. Simulations conducted by the authors reproduced the same number of bright galaxies observed by Webb, including both confirmed ones and overly bright candidate galaxies. If this is indeed the case, James Webb may have captured these young, bright galaxies at just the right moment. Alternatively, it could be a combination of various factors that together create this unexpected picture. Of course, we cannot rule out that further observations might compel scientists to revise some of their cosmological models, but it's important to understand that moving the date of the Big Bang would require far more substantial arguments than a few bright galaxies. After all, the fundamental principle of the scientific method remains unchanged and is beautifully summarized in Carl Sagan's famous words, "Extraordinary claims require extraordinary evidence." If some of the most distant galaxies are challenging to explain with current theories of their formation, the farthest structures they form fit these theories quite well. This is yet another remarkable discovery made with the help of James Webb, a baby galaxy cluster. Structures like galaxy clusters, of course, are not born in the mature state in which astronomers observe them in the relatively nearby universe. Instead, they must undergo an evolutionary process through a protocluster phase. Therefore, if scientists want to understand how galaxy clusters grow, they need to observe their beginnings. As part of another early scientific program called GLASS, Webb was directed at a region of the sky containing a well-known cluster called Abell 2744, better known as the Pandora cluster. This is an ideal location for finding something very faint and distant because the immense gravity of the cluster creates a powerful gravitational lens, acting like a magnifying glass. Even the most powerful infrared telescope benefits from the assistance of nature's gravitational forces to peer into the deepest parts of the universe. Astronomers were fortunate to observe 7 distinct galaxies here that photometrically displayed the same redshift. Eventually, this was confirmed spectroscopically. Each galaxy had a redshift of 7.88, corresponding to a universe just 650 million years old. Given that these galaxies are relatively close to one another, the region of space they occupy is about 20 times denser than the average matter density in that universe. This means these galaxies are bound in a cluster, the most distant cluster ever observed. The precise determination of redshifts also allowed scientists to measure the velocity dispersion of these galaxies, the speeds at which they move relative to one another. These estimates were around 1,000 kilometers per second, indicating an immense gravitational interaction holding the galaxies together. Using this data, scientists calculated the mass of the dark matter halo that serves as the framework for such structures. Based on their calculations, they modeled that the halo mass of this protocluster today could be comparable to that of one of the largest known galaxy clusters, the Coma cluster. In other words, what we now see as a collection of tiny red dots in the early universe could have evolved into a colossal structure containing thousands of galaxies. It might now be one of the largest clusters in the universe. Thus, astronomers have not just speculated, but have actually observed one of the steps in the universe's growth process. Scientists have long been puzzled by a problem that arose almost immediately after we began observing the universe within the first billion years of its existence. This problem is related to black holes. Although the physics inside black holes is strange and incomprehensible, scientists have a good understanding of how they form. Most commonly, they are the result of the collapse of massive stars' cores at the end of their lives, or for example, the merger of 2 neutron stars. There's even a hypothesis that many black holes were born alongside space itself during the Big Bang, but this is a rather exotic explanation that's hard to substantiate. Here's the intriguing part. Before the launch of the James Webb Telescope, the earliest known black holes were exceptionally bright quasars at redshifts greater than 7. Most known quasars have been observed at redshifts around 6, while the few seen in the earlier universe turned out to be true oddities. The issue is that they are surprisingly massive, hundreds of millions or even billions of solar masses. This wouldn't be surprising if we look at nearby galaxies. For example, the black hole at the center of M87 has a mass of about 3.5 billion suns, and Sagittarius A** at the center of the Milky Way is 4.3 million times the mass of the Sun. But in a universe just 800 million years old, such massive black holes are astonishing. The problem lies in the fact that no matter how much material they consume, black holes cannot grow as quickly as they please. There's a strict limit to how fast they can gain mass, known as the Eddington limit. If we assume these ancient massive black holes collapsed from stars, even ones 200 times the mass of the Sun, there just wouldn't be enough time for them to accumulate such enormous mass within a few hundred million years. In other words, it's hard to explain how they grew so much unless they were born already thousands or even tens of thousands of times the mass of the Sun. But how could they form in the first place? It's unlikely that even the first generations of stars could have been this massive. This, in essence, is the problem astrophysicists have yet to solve. One of the most intriguing hypotheses suggests that supermassive black holes could form directly from collapsing gas clouds, bypassing the stellar phase altogether. At least supercomputer simulations allow for the formation of black holes in this way, giving them substantial masses right from the start. Over hundreds of millions of years, they would gradually consume material and grow into the massive objects observed at redshifts around 7. To test this hypothesis, it would be helpful to find black holes in even earlier stages of the universe, with higher redshifts, and observe what evolutionary stage they are in. This is where James Webb played a pivotal role. In 2023, a group of scientists observing the gravitational lens of the Pandora cluster discovered a galaxy called UHZ-1. Its spectroscopically confirmed redshift was slightly greater than 10, meaning we are seeing it as it was when the universe was only 470 million years old. The galaxy itself is fascinating because it's so early. However, by observing it for 2 weeks with another space telescope, Chandra, researchers detected intense X-ray radiation. This is a hallmark of supermassive black holes, as the gas surrounding them becomes superheated and emits high-energy radiation. Given the brightness and energy released, the mass of this black hole is estimated to be between 10 and 100 million suns. This makes it yet another overly massive giant for such an early universe. Furthermore, based on the brightness of the galaxy itself, astronomers estimate its mass to also be within the range of 10 to 100 million solar masses. This means that the mass of the black hole is comparable to its host galaxy. This starkly contrasts with black holes in the centers of relatively nearby galaxies, whose masses typically constitute only a fraction of a percent of the total mass of their host galaxies. The extraordinary mass of this black hole, coupled with the X-ray radiation it emits and the brightness of the galaxy discovered by Webb, aligns well with the hypothesis that black holes can form directly from the collapse of gas clouds. One of the most distant black holes ever observed appears to fit exactly what scientists anticipated under this hypothesis. Essentially, by observing this object, astronomers are witnessing a brief stage in the evolution of both the black hole and the galaxy itself, when their masses are still relatively comparable. Over time, however, the galaxy will likely outpace its black hole in terms of mass growth. This is because new stars form more quickly than the black hole can grow by accreting matter. As a result, in this cosmic race, the galaxy might evolve into something more familiar to our eyes, with the black hole eventually comprising only a small fraction of the galaxy's mass. Of course, this doesn't mean the mystery is solved just yet. Much more data is needed before scientists can draw confident conclusions. But for now, the idea that black holes don't necessarily require stars to form seems plausible. Perhaps such black holes born directly from collapsing gas clouds reside at the centers of the largest galaxies in the universe. Well, to move on to another important scientific achievement we owe to the Webb telescope, we need to first say a few words about the observatory considered its predecessor. One of the 3 scientific justifications for building the Hubble Space Telescope was to use it to determine as precisely as possible the parameter known as the universe's expansion rate. Before the Hubble era, ground-based observatories produced significant uncertainty regarding this value. For instance, the age of the universe was estimated to lie somewhere between 10 and 20 billion years. Thanks to Hubble, astronomers were able to reduce this uncertainty to just 1% by using the telescope's ability to peer deep into the universe and measure the brightness of variable stars called Cepheids, as well as Type 1a supernovae. Their known luminosity allows us to calculate their distances, while their redshift indicates how much the universe has expanded between them and us. Thus, this method became a robust tool for determining the universe's expansion rate, which drives galaxies apart through cosmic expansion. However, there's a problem. This method yields a rate of 73 kilometers per second per megaparsec, while precise measurements of the cosmic microwave background radiation made by the Planck Space Observatory give a value of 67 kilometers per second per megaparsec, and no one knows why. This discrepancy is known as the Hubble tension. The inconsistency between the results of the two methods emerged in the early 2000s and has only grown more pronounced over time. It was initially thought that this discrepancy might be due to measurement errors, so it was expected that improved precision would eventually reconcile the two values. But they stubbornly refused to align. As a result, astrophysicists have been racking their brains over this issue, trying to find at least some explanation, searching for any tiny inaccuracies that could influence the observations. No one doubts the reliability of the Planck data, so the focus is usually on potential inaccuracies in Hubble's observations. One potential issue is thought to lie in determining the distances to Cepheid variables. It's been hypothesized that the brightness measurements of these stars may become increasingly inaccurate as their distances from us increase. In other words, there could be an error that grows with distance, causing increasing inaccuracies in the measurements. This could be due to the light from Cepheids blending with the light of neighboring stars. This effect indeed becomes more pronounced with distance, as densely clustered stars may not be resolved individually. Additionally, interstellar dust within galaxies further complicates observations, as Hubble observes the universe in visible light. But James Webb easily peers through dust, as infrared waves pass through it effortlessly. Naturally, Webb also has higher resolution. As you can see in this comparative image, individual stars appear much sharper. Therefore, Cepheids are observed more clearly, eliminating any potential inaccuracies. In 2023, a group of scientists studied 5 major galaxies with 8 Type 1a supernovae, as well as about 1,000 Cepheids within them. Their data did not refute, but rather confirmed that Hubble's measurements were accurate. It seemed that another potential source of error had been ruled out, yet the Hubble tension remains unresolved, as Webb confirmed the Cepheid distances. But this issue is still not settled. The thing is, there are studies where scientists used Webb to measure distances not only to Cepheids, but also to other standard candles, such as stars at the tip of the red giant branch and stars on the asymptotic giant branch. Interestingly, the average value provided by red giants aligns much closer to the Planck satellite's value, seemingly resolving the Hubble tension. But Cepheids do not. Ideally, we need to find galaxies containing several types of standard candles, Cepheids, supernovae, red giants, etc., to calibrate the distance measurements based on various sources. In practice, however, such galaxies are rare, and it will take time before more are identified. Therefore, it's still too early to say whether James Webb will solve the cosmological crisis. For now, we can confidently say that it has provided more tools to eliminate at least some of the potential inaccuracies in measuring object luminosities. For cosmology, this is an incredible new instrument, but it's not just for cosmology. Stay tuned for the next part, where we'll explore other fields of space science where James Webb has contributed to groundbreaking discoveries. Stars, planets, nebulae, and, of course, the solar system. All this and more will be covered soon, so don't miss it.